Alright, hi, my name is Effie, and today I'm going to talk about the internals of Room. I work for Quizlet, and let's get right through it. So, for this talk outline, I'm going to be covering the three parts that make writing to a database, which are the SQLite engine itself, the Android APIs, which are in the android.database.sqlite package, and Room and how it works on these two other pieces. And I want to give like a better understanding of how they coordinate with each other. So, and what we as developers should know and can do sometimes to have a better engineering experience and have a better interface with Room and with SQLite. And I'm going to be skipping a little bit back and forth between those three layers. I'm going to talk sometimes about a little bit of the internals of SQLite. I'm going to maybe sometimes talk about how the API interface looks like and how Room looks like. So a lot of these topics that are mentioned here, like threading, triggers, transactions, they're going to be covered from those three different perspectives. So the first thing I want to start with is an intro to SQLite. And SQLite is an embedded SQL database engine, which means it lives within our app. An instance of it is running within our app. It doesn't have a separate server process like other big databases like Oracle, etc. And it reads and writes directly to an ordinary disk file. And I'm saying like it is a single file. We can use regular SQL language to perform operations on it. And the fact that it's embedded also means that we can ship our own version of it. There's a version of it that's shipped with Android, but it is possible and done a lot of times to replace it with our own embedded specific in-version app of it. So this is how the architecture looks overall. The main takeaway from here is that SQLite works by translating SQL statements into bytecode and then running that bytecode in a virtual machine. So the top part is the interface which our APIs connect to. And the SQLite interface elements can be grouped into roughly three categories. One is objects. An object could be a database connection, which we'll talk more about in the future. Constants, which are just a list of constants that are being used, like result codes and flags and things like that. And functions, like a function that executes SQL statements. Below the interface, we see the SQL command processor. And that's where SQL statements are processed by SQLite into a bytecode program by using all the section in the right part, which is not super interesting for the purpose of this talk. And then the bytecode program created by this code is returned and then run by a virtual machine on a structure called a B tree for people who love CS stuff. This is how SQLite implements its storage on disk. And like I said, all the B trees are stored on the same disk file. It is a single file database. And the B tree model requests information from the disk itself, from the actual storage, from the file, in fixed size pages. And we have a model called Pager just below the B tree, which is responsible for reading, writing, caching these pages, locking these pages, doing all operations against the actual concrete operating system file. And we're going to talk a little more about them, about the pager in a little bit. So the second bit that sits on top of SQLite is our Android APIs and our androidx APIs. So our Android APIs live in the android.database SQLite package, and this is SDK framework specific and corresponds to the version that is sitting, that SQLite is on that particular Android device. On top of that, AndroidX has an abstraction which is just a bunch of interfaces that can either be implemented by the framework or are implemented by the framework, or can be replaced by anything else. So if you wanted to have an embedded version of SQLite and do something completely different with those interfaces, implement these classes in any other way, you could totally do it. Or reference, for that matter, reference your own embedded version. Again, that's possible through here. And then if you do want to reference, or your app is using the actual Android original implementation, these are the wrappers that wrap those implementations in AndroidX. And this is the top part of our layers, which is Room and Room architecture. Room is divided into separate models. And I gave the whole list on the left side. It's a little small, I know. But the very important ones, or the more used ones that we're going to see, are the Room common, which is the annotation interfaces that we're all using when we're using Room. We're using all the insert, etc. We have the Room compiler, which is the annotation processor. It has the basic class of Room processor, which takes all these annotations and creates all our generated code from everything that we annotated. We have the Room runtime, which is the core of the Room operations. It contains classes, for example, RoomDatabase, and it is a home to many classes that we'll see later in this talk. And we have the models for Room coroutines and Room RxJava, which are the hooks that we use when we want to use RxJava or coroutines on Room. Room itself doesn't have any knowledge of these concepts. So it will take, for example, an observable and do like whatever operations it needs to do on the Room runtime. There are hooks also to LiveData in the Room runtime. They're mostly specific methods inside there that do it. So that was the intro on the 3 layers, and now I want to dive into the first aspect of working with databases and working with Room, which is, let's talk about threads, processes, etc. Now the reason I wrote processes here is because for SQLite itself, there's no difference. SQLite doesn't care if you're using multiple threads or multiple processes. For it, the mechanisms are the same. It only matters for us because we're using Android. We're mostly using a single process, and we're mostly using Android APIs, and it's all threads for us. But every time you hear the word process, or you might see it, just replace it with threads for the SQLite bit, and you're all good. So like I said, we're going to start with SQLite, and we're going to talk about the very basic level of handling threads or handling different processes on SQLite, which is locking. And by locking, I mean lock the file itself that we're using. So we have the pager model that we saw earlier in the architecture scheme, and it controls the access for separate threads. And From the point of view of a single thread, or a process, for that matter, a database file can be in one of those 5 locking states. And the first one is unlocked, which means no one's doing anything, everyone's just relaxing, no one's reading from the database, no one's writing to it. The second type of lock is a shared lock, and this is read-only lock. So any number of threads can hold the shared locks at the same time. You can read many instances from the same file. But no other thread or process, for that matter, can write to that database while there is a shared lock or one or more active on the database. The third one, and you're noticing that we're escalating here. We're going through the least restrictive one. We're just upping it up to more and more restrictive locks. The third one is called reserve. And a reserved lock means that a thread is planning on writing to the database file at some point in the future, but right now it's not. It's only reading from the file. It's not doing anything. We'll see how that comes together in a little bit. And when are we getting this type of lock and the locks after that. So multiple shared locks, like I said, can exist at the same time, but only one reserved lock can be on the database at the same time. So this is basically saying I'm planning on writing to the database, but with this lock, new reads, new shared locks can start. The fourth type is pending. And pending means that the thread holding the lock wants to write to the database as soon as possible. It's saying, I'm ready. I want to write right now. I'm just waiting for all the other locks to clear out so that I can start writing. In this lock, shared locks can finish up whatever they were doing, but we cannot start new shared locks. And the fifth and final one, which is the most restrictive one, is this. I need to write to the database right now. I'm writing to the database right now. Only one exclusive lock is allowed on the file, and no other locks of any kind are allowed to be there. SQLite in general works to minimize the amount of time that exclusive locks are held. So when this lock is held, no one else can do anything. So we're trying to have that one happen as little as possible. So let's see how it looks like from SQLite perspective. We want to read from the database, read from that file. That's super easy. All I have to do is open the database file, get a shared lock, and if for any reason at all the shared lock can't be obtained right now, then it means maybe someone else is currently writing to the database and has exclusive lock on it or pending lock. Then just fail immediately and return SQLite busy. From a SQL perspective, there is no queue or synchronizing or anything like that. Now, writing to the database is more complicated. It involves more stages. The first one is to get a shared lock like everyone else. The second step is to get a reserved lock. I want to write in the near future. And like I said before, other shared locks can still happen at this point. But I'm saying I'm planning on writing to the database soon. There's just a few more steps that I need to do before that. The third step is write all the data to memory, which is as simple as it sounds. And the fourth one is write to rollback journal. Well, what does this stage mean? And to make things even more complicated, there are actually two things that can happen here. So let's talk about the rollback journal and what it is. So we said that when a process wants to change a database file, it records the original and let's start over. Okay. When a process wants to change a database file, The first thing it does is it will record the original unchanged database content in a different file. The different file is called a rollback journal. And the rollback journal also records the initial size of the database, and the whole purpose of this is in case something happens during writing to the database, it crashed, or something else crashed, I don't know, the entire device crashed, it can come back to this file and say, this is how the database should have looked like. It was in the middle of writing a bunch of things to the database. Let's ignore them and restore the database to where it was before this write began. So if a database is recovering or being reopened again with a rollback journal, then it means, oh, it crashed before finishing writing to the database. So now we're continuing, after writing to this journal, we're continuing with writing to the database itself. Now we have the original changes moved over to the log, and now we can write the actual changes to the database, which is done by getting a pending lock, which means I'm about to write all reads, please finish up. Get an exclusive lock, lock the file, no one can access it, and write to the database itself. At the end, which I forgot to put here, we also delete the rollback journal, assuming everything went correctly. We don't need it anymore. Now our changes reflect what we were going to write. Now, to make things a little more complicated, there is a new type of log that exists in newer versions of SQLite and in newer versions of Android, which is called the write-ahead log. Write-ahead log is significantly faster than the rollback journal in most scenarios. It provides more concurrency, which we're going to talk about and see why, because readers do not block writers, and writers don't block readers. So reading and writing can happen at the same time, and we're going to see how that happens. So let's talk about a little bit about well, and how it looks like. We said, we talked about how the rollback journal works by writing a copy of the original unchanged database content into a separate rollback journal file, and then write the changes directly into the database file. The wall inverts this. We are writing all the new changes instead of directly to the database. We're writing them to this log file. So the original content is preserved in the original database file, and the new data is appended to this other file. And that means we don't have to lock up the entire database while we're writing. It also means that multiple transactions can append to the end of a single wall file. And maybe another, and the other thing that happens is at a future point, which is defined by SQLite. What happens is the SQLite takes that entire log file and dumps it back into the database file. Since this happens less frequently than it would have been with the rollback journal file, we're getting way less exclusive logs on our database. So writes in wall would look like something like this. First, we take this new data and we append it to the end of our log. Then we call a special command called commit, which means that we're done with this particular write. We can do this with many types of, with different writes over and over again until we reach a checkpoint. And by default, SQLite does a checkpoint automatically when the roll reaches a threshold size of 1,000 pages, but this can be customized or changed. And then only at the checkpoint, write, take the whole thing, write it to the database file. Now reads get a little bit more complicated because when you want to read a page of content, you have to first see if it exists in the log. And if so, get the newest copy of the data from there. If it doesn't exist, we don't have those changes, then go back to the original database file and read it from there. Readers, there's also some optimizations made up on this. Readers can coexist in separate threads. So to avoid forcing every reader to scan the entire WAL file looking for pages, data structure called WAL index is maintained in shared memory, so it helps the readers locate pages in the WAL quickly and read successfully. And with all this, the main important thing to remember to sum this whole write-ahead log thing is that because writers do nothing that would interfere with the actions of readers, writers and readers can run at the same time. However, since there is only one write-ahead log, there can only be one writer at a time. We're going to move on and talk about another thing that is controlling how many threads are accessing the database at the same time, and these are the database connections. So if you remember the interface layer of SQLite, we talked about how some of the interfaces are objects or can be thought about as objects. And one of the main ones is a connection. It is represented by a pointer to an instance of a structure named SQLite3. It doesn't really matter for our purposes exactly what it is. It's just useful to think about it as an object because it has a lifetime. It can be opened and closed. And in this construct, in this connection object, operations on the database can be done. Selects, inserts, etc. Now, it's also important to know that SQLite provides isolation between operations in separate database connections, but not in the same database connection, which makes it even more confusing. And in the context of Android APIs, again, the same rule applies that only one write connection can happen and multiple read connections can happen at the same time. And again, if we're talking about app threads, they can also access and use the same connection and see the same data on that connection. Is that confusing? Yes, it is. If we wanted to get a connection to SQLite, we would call one of these two methods, get writable database and get readable database. They would actually go to the same place, which is the get database locked. And they would always try and get a writable database first, and only if it is unavailable, it would get a readable database. So basically, there's not a whole lot of points to manually call get readable database. You can always call get writable database and get either one. Depends on availability. And inside SQLite database, we also have our connection pool, which is all our available connections. Android does implement some Java locking in SQLite database to help us, or to help keep things straight and make sure that we're locking the threads between operations. You can see the pool itself is thread safe. It's not super secure. There are ways to definitely get deadlocked on database threads and on connection flows. So if we go about and we are saying, okay, now that we know the difference between rollback journal log and write-ahead log, and we want to change our settings, and we would like write-ahead logging better, which is mainly usually the case, because it is faster and it does allow for more reads to occur at the same time. This is the method that we would call on the framework's API, enable write-ahead logging. And this method does actually two things. One of them is it changes the settings directly on SQLite engine. And the other thing is that it would change the connections and how many connections read and write are allowed at the same time. It does use more memory to enable write-ahead logging because we are holding references to more connections at the same time and whatever data they hold. And the maximum number of connections used is dependent on device memory and other properties and can also be played around with. So if we look at the internal implementation of set write-ahead log mode from configuration, we would see that what we're basically doing here is we're executing a SQL command, and it's a special SQL command called pragma, which changes the actual setting of the database. And in this case, it's changing journal mode to a new value, which, if it's write-ahead log, would be well. And Room does this by default. So this is where Room comes into the picture. And we sort of start seeing the connections. Room is saying, and rightfully so, write-ahead log is so much better than our old-fashioned rollback journal that we just want to enable it whenever we can, which is any API above Jelly Bean. We are going to call our API and set write-ahead logging. So up until now, it seems like threads don't matter much to us as developers. We can do multiple reads. The connection pool will take care of things for us. We can talk a little bit about writes. We're going to talk a little bit about how Room does reads and try and move up from our very super basic core level. In general, queries or reads in Room are free to run on any background executor configurable by the developer. So if we're using RxData, or if we're using RxJava, or we're using LiveData, we're using futures, this doesn't matter too much to Room. But what about writes in Room? How do they work in terms of threading? And the next concept we need to understand in order to sort of understand that is how transactions work and what are transactions. So we're going to dive right back in and look at transactions in SQLite, but this is way quicker than the locking mechanisms. SQLite is transactional, and a transactional database means that all the changes that we're doing to it are atomic, consistent, isolated, and durable. And SQLite itself implements serializable transactions. And even if a transaction is interrupted by a crash or anything else, then we can recover from it. SQLite, by default, is in something called auto-commit mode. It means that for each command that we're executing against it, SQLite starts, processes, and commits the transaction automatically. So if we're just doing a write statement, an insert statement, or an update statement, SQLite will commit it immediately. It will do it. It will do the auto commit itself. The SQL command begin transaction is our way to get out of this auto commit mode. If we don't want to do a separate transaction for every insert we want to make, we will use this command, begin transaction. Begin transaction doesn't acquire any logs on the database. It is saying, okay, you're going to do a bunch of things at once. So I'm not going to start committing them or writing them to file, either write ahead log or whatever. After every insert, you're going to do it all in one chunk. And then when we're saying commit, we're actually saying, okay, we're ready to go back to auto commit mode. We're ready to, we created a bunch of changes. They were all written just to memory at this point, and we're ready to save them all at once to our database. So if SQLite is an auto commit, like if we're not using transactions at all and we're performing a bunch of inserts or a bunch of updates or a bunch of any kind of transactions, it means that we're making our journal log even worse, because it will log the file for every write. But even with write ahead log, it's not ideal, because we're still going to write a lot of things to disk, and we're going to do this over and over. So transactions help us with multiple writes. So in Android APIs, all writing operations, and it doesn't matter if it's in a big transaction or an auto commit, will be serialized, which means that threads will wait for the connection. There's one write connection, and threads will wait on it when they want to write, if there's more than one write. Room wraps a lot of these things in transactions. And we'll see a little bit of that. We'll see a lot of that later. So the one example for an optimization that Room does for us is that it batches multiple write statements in the same transaction. It does this for the same entity. So if we're inserting, 5 things of the same DAO that we're using, Room will wrap them up in the same transaction. It will go do the begin transaction, go in a loop for all of our entities, commit them all together, and then call end transaction. The next topic I want to talk a little bit about are triggers. I know I'm jumping a lot around, and you're going to see how all of this comes together in a little bit. Triggers in SQLite are database operations that are automatically performed when a specific database event occurs. They are events, basically, on the database level. And what we're saying is in SQLite itself, we're defining a behavior that says something like, if a row changed, do something. Or if an insert to this table happened, do this other operation. These are all database level operations. So for example, we can say, if addresses table was changed, do something on people table, or something like that. These are all database changes. In RxJava and LiveData, triggers are used by Room to track changes to the database and let us know, because we are using RxJava and LiveData to observe those changes, and we sometimes want to know when an entity has changed or when a new entity has been inserted and things like that. So I'm going to look at this from the perspective of LiveData, but the same mechanism basically applies for RxJava. And what is happening is we have a room tracking LiveData, which is our special customized object for tracking and getting results from changes that happened in the database on specific things that we define on our data. In this, we are using something called a class called Invalidation Tracker. And the Invalidation Tracker is the tracker that is responsible in Room. It's the implementation of Room of all these trackings. And again, hooking those RxJava observers and the LiveData into the database itself. And inside the Invalidation Tracker, say we are now observing something that we haven't observed before, we are going to do something called add weak observer, which will add us a new mechanism to track that observer and know if something in the database level itself has changed. So now we can say that Room adds triggers to the database itself. So say we are saying we want to track when a new entity has been added to our table. Room will create a trigger on that table that says notify when a row was added. And the way it does that is it creates a temporary table, a different table that is only accessible and only Room knows about. And the syntax of the trigger will be something like, whenever a row is being added to this table, add a row in our temporary table. And every time there is a transaction happening through Room, a different transaction, every other transaction that happens afterwards, we are going to call check update table, which is our special table that contains all the entries from all the triggers. And we're going to see, is there an entry there that is important to us? Is there an entry there on the observable, on an existing observable that we have right now? If there is, we're going to notify that. So this is basically, again, the same logic. We're saying at end transaction, get me refreshed versions async. Go ahead and check that table for me. Tell me if in this table there is or isn't information relevant to me, which means that data has changed. And then we're going to go back and see what data has changed and notify that observer. Now, this is another sort of optimization that Room does on this kind of table. And so what happens here is that basically transactions, they make the write-ahead log bigger because, again, all the writes to triggers, to temporary tables, all these things, they're going to be added to the write-ahead log. So we are even more in danger of reaching the limit of how big a transaction can be. And in order to sort of alleviate that, if we are doing more than one insert, if we're doing like 100 inserts, we're only going to change the tracking table once. So if within the same transaction we are adding 10 entities, there's only going to be one line added to the database. So In Android SQL, API transactions are exclusive and thread confined, basically meaning threads would wait upon each other if they tried to concurrently do transactions. And this was improved by Room by, instead of making queries with transactions wait on each other, serialize them in such a way that multiple threads are not consumed, because we're just going to reach a lot of deadlocks there. And that executor is a new executor that is called transaction executor. And this is only for actual writing to the database when calling this context, because it is single threading. And this is how it looks. It's basically just an executor. There's not a whole lot to do there. And if we're looking at examples from RxJava, for example, we'll see here that we're doing observe on and subscribe on schedulers, and we're getting those schedulers from the database executors, which will be a query executor if it's just a read, and a transaction executor if it's a write. And the same would happen in coroutines, slightly more complex. Would get the transaction dispatcher and would decide where to dispatch it on. And if you're wondering what are the transactions APIs in Room that are both auto-generated by the code that we're writing or can be used directly. So we have 3 that are existing in our Room database. The 2 older ones that are sort of being deprecated are begin transaction and end transaction. And the 3rd one that is our new one is run in transaction, which does begin transaction and end transaction. So what we can do is just use this one instead of using both begin and end and potentially forgetting to end it or needing to use 2 APIs. Run in transaction is synchronous and blocking. So with the auto-generated code, and I mentioned this again briefly a little earlier, it decides whether to use a transaction executor or not. It depends if we have a return type that is async or not, and if we have just a query, or do we have an actual modification to the database. If we're using, or if someone's using the run in transaction APIs directly, or using transactions directly, use run in transaction, because like I said, this will make sure it runs on a thread-safe environment. And also make all the transactions relevant, meaning don't make any other operations on them, because this will again block, and make them as small as possible. To sort of sum it all up, it is safe to do multiple reads and writes in multiple threads. An Android SQLite layer will take care of creating sessions for each thread. And more specifically, SQLite implementation will block threads if all connections in the pool are used. From Room's perspective, the transaction use and transaction mechanism that we saw is the best way to go about it. And I guess let's stop here. I do have a little bit more, but we're running out of time. So.